Good morning. This is a quick video lesson on acid-base neutralization problems with respect to solution stoichiometry and also dilution problems, which has a direct relationship to m times v equals the number of moles, which we've talked about for the past couple days. So just a quick reminder, we've talked about acid-base neutralizations in the past. Remember that acids are chemicals that have H plus in the front, shown by, H2SO4, something that's called a diprotic acid. So it has two hydrogens in front. Bases are chemicals that have OH minus and give up OH minus to solution. Remember, when those two come together and neutralize, they form water, the H plus from the acid and the OH minus from the base, and some other chemical, usually a salt, and it is a double exchange reaction. So again, this is the overall neutralization expression. H plus and OH minus yields water. So a couple of quick problems, and they're solved exactly the way that solution stoichiometry problems are solved. So let's do this one as an example. So first, what volume of 0.2 molar hydrochloric acid is needed to neutralize 100 mils of 0.1 molar NaOH? Well, first things first, of course, we need a balanced chemical equation, right? So we've got HCl and NaOH. I'm not bothering with states of matter here. And what's nice about this, a very simple expression, is that it's all 1-to-1. This is a balanced chemical equation with sort of understood ones as part of the stoichiometry. All right. Now, the only thing we know here is, remember, m times v. And m times v is equal to number of moles. And this is the only information we have on that. So we're going to have to use m times v for the base to figure out the volume of the acid, which is what's asked. So we take NaOH, m times v, and we take what's given, 0.1 molar times 0.1 liters. Remember to convert milliliters to liters in this case. And so that's 1/10 of 1/10, or 0.01 moles. All right. Now, notice, let me undo that. Notice that this stoichiometry is, there's understood 1-to-1 here. So if we know moles of NaOH, and we do right there, that means we know moles of HCl needed to neutralize that, which is 0.01 moles. So we go back and we use m times v a second time. All right, m times v is number of moles for HCl as well as NaOH. Remember, 1-to-1 stoichiometry. So if we have 0.01 moles of HCl, we can substitute some values in. So we knew the molarity that was given in the expression 0.2 moles, shown right there. Okay, and we multiply it by volume to give number of moles, and we just figured out number of moles, because it was number of moles of the NaOH, and of course they're equal because of 1-to-1 stoichiometry. The one thing we don't know is the volume, but that's an easy problem to solve now. That's an easy algebraic problem. So solving for V, it's 0.01 divided both sides by 0.2, and 0.01 divided by 0.2 is 0.05, and that's in liters, remember. So if you need to, convert to 50 milliliters. So pretty simple stoichiometrically. Let's do a slightly harder one, but exactly the same process. What volume, so we're going to have to solve for V, of 0.02 molar HCl is needed to neutralize, and here's where we have m times v, 0.035 molar and 200 mils of calcium hydroxide. So again, you need a balanced chemical expression because you're going to need that stoichiometry. And let's do m times v of the thing we know, 200 mils of 0.035 molar calcium hydroxide. So that's shown here, m times v, and that comes out to be 0.007 moles of calcium chloride. And then we have to take calcium chloride moles right here and convert to hydrochloric acid moles. And notice you'll get twice as many moles of hydrochloric acid as calcium hydroxide to neutralize that product. So take a look down here. We start with moles of what we know, the calcium hydroxide, 0.07. We multiply by 2/1. That's the stoichiometric coefficient. And we end up with 0.014 moles of HCl. And then the question asks, what volume of 0.2 molar HCl? Well, again, we use m times v a second time. Remember that m times v is equal to number of moles, and we now know number of moles of HCl. And we also know the molarity. Okay, what we don't know is the volume. So if those values are substituted in here, we had 0.02 molar, again, given in the question, sort of verbally, that clue is given. All right, let me scroll back down. So this is m times v, and the only thing we don't know is v, because we figured out number of moles. And so again, a simple algebraic problem to get to the answer. So solve for v, substitute the values in, solve for v. Good. All right. Now, lastly, so again, let me just go back. This is exactly the same as any other solution stoichiometry problem. You need to figure out a balanced chemical expression, and then figure out number of moles of each reactant. And in this case, we just do m times v to equals number of moles. And then we go through the regular steps of solving a solution stoichiometry problem. That's shown here. Okay, determine the limiting reactant. We don't have to do that in neutralization expressions, because in a neutralization expression, you always have the precise amount of moles. Nothing's really in excess or limiting. In any case, then convert moles of your limiting reactant to moles of product, and then to mass of product. All right, sorry, back to this. Now, sorry, let me scroll forward. We want to get to here. Dilution problems. Now, dilution problems in the lab are usually because chemists, when they buy volumes of a reactant, let's say sulfuric acid, they buy it in very high molarities, what's called a stock solution, shown right here. And a stock solution is generally a super high, often dangerous molarity. So as an example, don't write this down. You don't need you need to, but the hydrochloric acid I buy, usually for a year or even 2 years worth of chemistry experiments, is as high as 12 molar, extraordinarily dangerous chemical. Sulfuric acid is 18 molar. So these are chemicals I will never let a 10th grade chemistry class work with, because they're just so dangerous. So most of the experiments we do are something on the order of like 2.5 molar. So the question becomes, how do you go from an 18 molar stock solution and dilute down exactly to 2.5 molar? You have to be able to do some calculations and figure out what volume of the 18 molar that I need. Okay, so water added to the stock solution will of course lower the molarity. Okay, but that's the question. How much water do you need to add? So let's do a thought experiment first. So notice on the left, we've got two beakers here. On the left, we've got our stock solution. This is how concentrated HCl is received at St. Albans, for example. And that's usually enough to last me a year to even 2 years of chemistry problems, chemistry labs. So we've got 10 mils of 12 molar HCl. So we could do m times v and get number of moles here on the left. And then we're going to dilute that by a factor of 10, so we end up with 100 mils of the same thing. Now notice we've added water. Does the number of moles of HCl change from over here on the left, 10 mils of 12 molar, to over here on the right? The answer is no. HCl remains exactly the same, because the only thing we've added is water. All right, so if we can calculate the number of moles on the left, we can set it equal to number of moles on the right. And that's exactly what we do. So notice, on the left, we started out with M1, which I'm going to call M initial, the initial molarity, of 12 molar HCl. And we had a volume, 10 milliliters. Convert that to liters, of course. And we do M times V to get the number of moles of HCl. Right? And as I said, moles of HCl on the left is equal to moles on the right. We've just added more water. So now we know m times v is equal to number of moles, and we know the number of moles. What we don't know is the final molarity of that solution. Now, you can probably guess it, right? Because we went from 10 mils to 100 mils. So we're diluting by a factor of 10, which means if we started with 12 molar, we're going to end up with, this is a guess, I'm going to say 1.2 molar. Okay, let's see if that's the case. So again, m times v is equal to number of moles, and we know the number of moles right there. So that's shown here, m2v2, which means final conditions. All right. We know the volume, 100 mils. The thing we don't know is the molarity. At least we're pretending we don't know right now. So you'd end up with an expression that looks like this. M2, whatever that new molarity is, times 100 mils is equal to 0.12 moles. And when you do that, you end up with a molarity of 1.2 molar, which is exactly what we expected. So back to this slide. Remember, the moles of solute in the final dilute solution is equal to the moles in the initial concentrated stock solution. You just added water. So you didn't change the number of moles, although you definitely changed the concentration. So just remember, m times v is number of moles, right? So we're going to put that to use because the initial m times v, number of moles, is equal to the final m times v, or number of moles. So that's a red box formula right there, m1 v1, and you can think of that as initial conditions. The molarity you'll know because that'll be the stock solution, highly concentrated. What you probably won't know in most of these problems is v1, the amount of stock solution to add to a sample of water to get a final molarity. And that's what's nice, is that in these problems, you will know both of these things. You'll know, for example, I want 250 mils of a 0.5 molar solution. So you know final conditions in that case. Okay, so that's the way I usually approach these problems, is that M1 and V1 are initial stock solution conditions, of which we'll know molarity, but maybe not the volume. But we'll definitely know what we want to end up with, right? As an example, 500 mils of 2.5 molar sulfuric acid. Okay, so M1, V1, number of moles on the left, is equal to M2V2, number of moles on the right. Let's do a couple of quick example problems. Okay, so here's one. What volume of 12 molar HCl stock solution should be used to mix up 500 mils of 0.4 molar HCl? So we know initial molarity shown right here. So that I'm going to put that on the left. You guys know how I like to write out my variables. So M1 is 12 molar. V1 is what we don't know, what we're trying to figure out, the volume of that 12 molar HCl we'll need to mix up the final conditions shown here. 500 milliliters, or 0.5 liters, of 0.4 molar stock solution. And then we just take M1, V1, and we set it equal to M2, V2, and we multiply the things out that we know. Initial condition here, final condition, and the only thing we don't know is the initial volume of that stock solution. So simple algebra is all you need to do to solve this. And the answer I got for this one was 16.7 mils. So what I would do is pour out 16.7 mils of the 12 molar stock, put it in a beaker, and then dilute up to 500 mils. And that should, according to the math, end up being a 0.4 molar stock solution, a 0.4 molar solution. All right, let's do one more. So another one exactly the same. What volume of 18 molar H2SO4? That is something I will never let you guys mess with because it's extraordinarily dangerous. But it's probably safe for us to use 2 or 3 molar sulfuric acid. So what volume of the initial stock solution, highly concentrated, do I need to mix up 250 mils of 0.2 molar solution? So once again, I love to write my variables out. So let me show that. So M1, the initial molarity, is 18 molar. V1 is what we don't know, what volume of that. What we want to end up with is M2, V2. 2 molar solution, 250 mils of that. All right, so plug and chug, right? M1V1, number of moles before, is equal to number of moles after. We throw the numbers in, and we solve for the initial volume, which is what? 27.7 milliliters. So again, I would take 27.7 milliliters of that initial sulfuric acid with this high concentration, 18 molar, and I would dilute that up to 250 mils using water, because that's my final conditions. And my final molarity, my final volume of the stock solution is what we wanted to solve for here. All right, that's a very quick video solution. There's lots more example problems in the class notes, so I urge you to look at those, and we will definitely practice these before the quiz. All right, thanks everybody. Good night.